Now that we've mastered the derivatives of specific trig identities, let's apply them to a variety of problems. So first let's find the derivative of y equals 2 sine of x. So by the constant multiple rule, the derivative of this would be 2 times the derivative of sine of x is cosine x. How about another one? Y equals sine of 2x. Now this is an example where the chain rule is necessary. When we take the derivative of the sine of something is the cosine of that same thing. But this whole thing needs to be multiplied by the derivative of the inside, which is 2. And so our derivative would be 2 times the cosine of 2x. One that relates them both, y equals 2 times the sine of 2x. Well, the derivative here would be 2 times the cosine of 2x times the derivative of the inside, which is 2. And so altogether our derivative is 4 times the cosine of 2x by the chain rule. Last in this series, y equals sine squared of x. Well, by the chain rule, the derivative of this would be 2 times the sine of x. But now I need to take the derivative of the inside, which is cosine x. And if you're having trouble seeing this, remember that sine squared x is the same thing as the sine of x squared. And that might be an easier way to see why the chain rule is necessary. Let's look at one involving a square root. So y equals the square root of the sine of 2x. I'm going to rewrite this as the sine of 2x to the 1/2 power. And now I'm going to end up using the chain rule multiple times. So if I start from the outside, by the power rule, I'll have 1/2 times the sine of 2x to the negative 1/2. But then I need to take the derivative of the inside, which is sine of 2x. So its derivative would be the cosine of 2x. But then I have another inside, and that second inside, it's hard to see without the parentheses sometimes, is the 2x, and the derivative of 2x is 2. And cleaning this up, we would find that the derivative is going to equal the cosine of 2x over the sine of 2x to the 1/2 power. A few more examples. Let's consider f of t equals t times the cosine of t. Taking the derivative of this, I'll need to use the product rule, because this is t times the cosine of t. The derivative of t is 1 times the cosine of t, plus, by the product rule, t times the derivative of cosine t, which is negative sine t. And cleaning this up, this will become the cosine of t minus t sine t. The next problem for us to consider, let's look at y equals 6 times the cosine of x squared. And I'm going to put the parentheses around the x squared to help me recognize some chain rule issues here. So the derivative of the whole thing will be 6 times negative sine of x squared, and the derivative of the inside, x squared, is 2x. So cleaning all of this up, we have negative 12x times the sine of x squared. Another example to consider, what about y equals 1 plus sine x over cosine x? Now we could use the quotient rule as it stands. What I see though is I can rewrite this as 1 over cosine x plus sine x over cosine x, and that is equal to, well, 1 over cosine x is secant x, whose derivative I have memorized. Sine x over cosine x is tangent x, whose derivative I also know. And so y prime in this case will be equal to secant x tangent x, because that's the derivative of secant x, plus the derivative of tangent x is secant squared x. Right, so just a different strategy rather than the quotient rule, which would have gotten you an equivalent but perhaps different expression. Two more examples. Let's consider y equals secant cubed of 2x plus 1. So a lot of chain rule here. The derivative of this by the power rule, to get started, would be 3 times secant squared of 2x plus 1. But now I need to take the derivative of the inside, and the first inside is the secant of 2x plus 1. And the derivative of secant is secant tangent, so this will be times the secant of 2x plus 1 times the tangent of 2x plus 1. And now I have a second inside, which happens to be 2x plus 1, and its derivative is 2. So it's kind of messy using the chain rule, but it works. Cleaning this up, this will become 6 times the secant cubed of 2x plus 1 times the tangent of 2x plus 1. Last example for us here is y equals the cube root. Actually, no, let's not do that one, let's do a different one. Let's do y equals 4 times the secant of 3x times the tangent of 3x. Try and delineate this so it's a little easier to see. By the product rule, y prime, nope, alright, we'll start over. My slide got erased. That's okay. So again, what we were working on was y equals 4 secant of 3x times the tangent of 3x. When I take the derivative to find y prime, I'll be using the product rule. And at first, this will be 4. The derivative of secant of 3x will be secant 3x times tangent 3x. And I need to take the derivative of the inside, so times 3 times the second function, which is tangent 3x, plus, I'll have 4 secant 3x times the derivative of tangent 3x, and the derivative of tangent is secant squared, so this will be secant squared 3x times the derivative of the inside, which is 3. Cleaning all this up, y prime will equal 12 times the secant of 3x times tangent squared 3x plus 12 times secant cubed of 3x. So there's a variety of examples of taking trig identities and having to recognize and use the chain rule, sometimes quite a bit.